Okay, so yes, thank you, Frank, and thank you all the team for organizing the webinars and for inviting me. It's quite an exciting opportunity to present this. So yeah, I work at the University of Bergen as a postdoctoral researcher, but today I'm actually presenting something that I have done almost 2 years ago, but it was a very nice experience that I had in the University of Barcelona, working mainly with the UiB, but also with other people there, and doing some analog modeling, some 3D, really 3D analog modeling of salt tectonics. And yeah, this talk and the work we've done there is looking at the effects of basal relief and the salt basin geometry on gravity-driven salt tectonics, or salt-bearing rifted margin salt tectonics. Yeah, so just a quick introduction about the process of salt deformation on passive margins or rifted margins. Salt is deposited usually in the last stages of rifting or just after rifting in most cases. So deformation is usually driven by gravity, by two main processes. The first process is the gliding. Actually, let me just do that. So I have two primary drivers of salt tectonics in those settings. Gliding, which is actually the slope of the salt basin, which is usually dipping regionally seawards, and spreading, which is the loading of sediments, so differential loading of prograding sediments, of post-rift sediments. And in both types of deformation, we have these kinematically linked domains of up-dip extension with normal faults and some extension of diapiers, and down-dip or downslope shortening or contraction, which can be in form of buckle folds, diapier squeezing, and thrusts as well. And also in these systems, you usually have an intermediate domain of translation. So both salt and overburden translate laterally, seawards. And with both gliding and spreading, we have this sort of distribution of domains, although you can have some difference in terms of structure styles or the magnitudes of deformation. But overall, you have up-dip extension, down-dip shortening. And here's an example from the Rhone fan. It's a very simplified, well-behaved salt basin system. We have very clear zone of extension here with normal faults, some of these salt rollers, which are these extensional diapiers, and have the down-dip contraction domain or shortening domain with some buckle folds and some squeezed diapiers. And the intermediate domain, which is broadly undeformed, have very mild salt deformation, some salt anticlines, but not much going on. And you can see here in this example, have a relatively smooth, very flat, well, it's deep in base ward, but it's flat base salts. And here's a physical model from Tim Dooley showing this sort of arrangements between up-dip extension, down-dip shortening, very simplified, but very clear message, very easy to distinguish these two different domains. And we see again, these domains connected by a zone of translation. And you can readily see that this is very flat, very smooth base salt. So there's not really much topography there. And you can quickly imagine that reality in rifted margins is much different. We have a lot of structural relief in the pre-salt. This relief is usually inherited from the rift stage. There's not really a lot of faulting or rift-related extension during the salt deposition. So it's just relief that was underfilled during the rift. So you keep the relief for the salt deposition. And that affects the post-rift salt tectonics evolution. So you see this example here from the West African margin. They have a lot more complexity, especially associated with these base salt highs or steps. And things are much more different than what we see in this simpler scenario here. So base salt relief, it can be a product of many things. In rifted margins, it's really typically rift structures like faults, horst, grabens. In a few cases, you can also have pre-salt folds, an example from the Levant margin in the Mediterranean. It can also be at least partially associated with irregularly eroded pre-salt topography and volcanic edifices or seamounts. And an example of a volcanic associated basal relief is from the Western Mediterranean, where we have the seamounts. And here's an example from the Campos Basin, where we have this basal horst or high. You have this basin wall dipping ramp at the base salt, and then you go into a more flat, but not fully flat base salt. And these affects the salt deformation, but also the distribution of depot centers and mini basins in the overburden. And the main consequence of basal relief, we now know this from some of the physical models, some of the pioneer work on the effects of basal relief from Tim Dooley and the AGL group. Ollie is one of them. Is that the basal relief, so this basal topography can disturb the regional flow of salt and cause salt flux variations. So, for example, if you move into a structurally elevated area, we go from an area of thick salt and then going into an area of thin salt, and that causes this salt flux imbalance. So you have salt inflation, you uplift the overburden, you can develop buccal folds or shortening features. And then you have the opposite in the other side of the horse. And as you progress, the formation can actually reactivate this inflated zone with extension. So we have this multi-phase history of deformation, most of it controlled by basalt relief and salt flux variations. In these early models, Tim Dooley and collaborators, they really address the effects of basal relief associated with lateral seaward translation of both salt and overburden. So mainly looking at the gliding process, not really into the spreading process. And the focus of the talk, I mean, is a lot about the modeling itself, but we use one very interesting, I think one example that is really close to my heart, at least. I've been working with this basin for quite a lot of time, and it's very interesting in this, structurally interesting. There's a lot of variability. There's a lot of interesting questions and a lot of debates on the salt tectonics evolution, but also the rifting evolution of this basin. So the Santos Basin is here located in the southeast of Brazil. You can see here the salt tectonic domains have an up-dip zone of extension here in blue and an area of inflation or contraction, but actually deformation is in reality much more complex than just one simple style of deformation. These polygons here represent the seismic data we use in these studies. We have both 3D and 2D data. I have some data that are actually cross-cut the entire basin, 2D lines. And there are two main features, and I'm going to show a cross-section here that I think explains better than the map. There are three very famous, very debated structural domains, very important for the point of view of exploration as well, which are the São Paulo Plateau, which is this area that's characterized by a very prominent basalt high, the outer high. Further landward, you have the landward edge of the São Paulo Plateau, of this inflated salt plateau. We have the Albion Gap, which is a very controversial area. It has been topic of debate for like 3 or plus decades. And it's an area that we have this 50 to 60 kilometers wide gap of the Albion interval. And I didn't mention before, but the salt is absent on age, and you have the Albion, which is the next sequence, and it's mostly carbonate, and is largely absent throughout almost the entire length of the basin for a very wide area. And this Albion Gap has this very remarkable rollover, which is a basin-wide dipping rollover, so it's counter-regional rollover, and with a lot of complexity and a lot of debates. One of the main debates about this is what is the origin of this large gap. It's quite hard to explain why you don't have Albion deposited for this very large area, more than 50 kilometers wide and almost 500 kilometers long. So there are two main end members. One is the extension model. So here the Albion is deposited almost continuously, and then as you translate salt and the overburden, you extend and develop this rollover. And the footwall of the Albion Gap, we have here the CFF, which is the Cabo-Frio fault. The key difference here from the expulsion model is that the footwall of the Albion Gap moves laterally, seawards. And in the expulsion model, the Albion Gap is already formed, at least most of it formed at the time of the Albion deposition. So you have a large diapia that doesn't accommodate any Albion deposition on top of it. And then this rollover forms by just expelling salt seawards without any or significant translation of the footwall. So this is one of the questions you want to address with this study. This is just a seismic example of what I just shown. And one thing that people haven't really looked in the context of the Albion Gap and the São Paulo Plateau is this very impressive fault or graben, which is the Melusa fault and the Melusa graben as well. What is the role and how does it interplay or interact with the Albion Gap evolution, and also how does it affect regional salt tectonics in the study area? And I didn't mention, but the Merluza Graben kind of overlaps from a good part of the Albion Gap in the southernmost part of the basin. And actually see there's quite of a good match between the orientation of the gap and also the dimension of the gap with the Merluza Graben. So the key questions we want to address is, what is the influence of the basal relief on the evolution of the salt and overburden structures? How is the interplay between gliding and spreading and basal relief? So expanding on the previous studies, we also want to address the role of spreading, and how is the interplay between these three different structural elements in the Santos Basin. So for that, we use this 3D sandbox model. So as I mentioned before, I had a really good time visiting Barcelona and learned a lot about it all and others there. Learned about the process of running physical models, and I can say it's very interesting, but it's also very laborious. It takes a lot of time, a lot of effort, but it's also really good fun, and it's really good to see things evolving, deformation evolving through time. So it's a very useful learning experience. For me, it was very interesting in that sense. We expand on the previous works from Dula et al. So they use more symmetric basal geometries. We now use something that is a bit more symmetric and more specific to the case study, so the Santos Basin. And we also start addressing the role of not only gliding, not only tilting the salt basin seaward, but also by the differential loading of the post-salt sediments. So here is the 3D model setup. You can really see this 3D because we changed the orientation of the subsalt relief laterally. So have a north domain where the relief is orthogonal to the transports to salt flow. And in the south domain, you have these two largest steps of basalt faults. They are oblique. So we construct the basal relief. It takes a lot of time to do that, a lot of sand as well. We spent about 2 days to actually have all of this done. Add the silicon and the salt, which represents the salt. And we have a pre-kinematic layer here, which we call the early Albion, as compared to Santos. And then we start the model by tilting the model further 2 degrees basinward and start adding the progradational sand wedges. So I can show you the evolution of the model with this map view, overhead evolutions. I'm actually gonna just animate the ends of it. Oops. Okay, yeah. So the initial stages, the early Albion, so the first wedge we start to deposit. We have very minor extension here in the up deep end of the model. We have a zone of inflation and uplift that's fully controlled by the Graben geometry. It's very kind of rectangular, blocky, and it fully fits within the Graben. As we progress the formation, we amplify the extension. We also migrate the formation seaward as you prograde, as sediments prograde. This initial zone of inflation is amplified, but because the Graben is narrower and orthogonal to flow, we have more uplift in the north, and that actually favors this diapia. We help the diapia also by removing some of the sand that is above this regional datum. And in the south, we have a much broader but more subtle uplift and inflation. As we progress the formation, we actually prograde sediments further seaward. The formation is amplified on most of the structures, and the diapia that formed earlier, it starts to move beyond the Graben. So most of the system is actually translating seaward beyond these basalt steps. And here's the cross-sectional representation of the basalt. We start to develop more significant folds over this subsalt high or the plateau here. But in the beginning, we actually have very little deformation there. And as we progress, the diapia starts to leave the Graben and move on to the salt plateau. And the diapia is going to flick between phases of shortening or narrowing and then widening as you move through these different basalt steps. And you can see these in the next stages. So now the diapia fully leaves the Graben and starts to advance, and it becomes significantly wider. And as you approach the other basalt step, it continues advancing, but now starts narrowing. And then there are also a lot of the complexities, but I think I don't have much time to talk about those. But the diapia also coalesces laterally of all the features forming in the south. And throughout most of this diapia history, it's bounded on its proximal flank or the landward flank by this expulsion rollover, whereas most of these other features are mostly extensional rollovers or normal faults. We can see also the evolution of this diapia and the whole system through digital image correlation and measure the strain. And I think I just want to highlight here the evolution of the diapia. And you see that the diapia has parts of the diapia that are under extension, and parts of the diapia that are under shortening. And that is largely related to how it flows over this basal relief, but also how it relates with the prograding wedge. And you can see flicks, if we go to the C and D here, flicks from periods of shortening and extension. Okay, and the cross sections, I think they sort of more visibly impact, sort of greater visual impact, and I think really nice to see the comparison of the cross sections with the real data as well. So I show here two cross sections, one in the north domain, so the basal relief is orthogonal to regional transport, and one in the south. And we can look at this and at least one of the regional profiles, and I think the key thing here is to show that at least the first order geometries are really good fit between the model and the real data. We see that the Albion gap has a very similar geometry, which has this turtle structure, which is a hybrid structure because it has a flank that is driven by extension, associated with extension or rollover, and the seaward flank with expulsion rollover, bounded by this diapia, very large diapia basinwards. We also have a similar style of deformation within the graben itself, which is mostly extension, some extension rollover. There's some differences in terms of style, a bit of a flip-flop or flicking between basinward zipping and landward zipping normal faults or rollovers. And yeah, the location of the Albion gap also matches. So the location, the geometry, and the dimension of the Albion gap also matches a lot with the data. And the São Paulo plateau is very similar as well. We have this domain of broad, of mild deformation, but mostly folding and salt inflation with a few mini basins. Just showing a few more cross sections and looking more into the detail of the Merluza graben and the Albion gap. And one thing our model, I think, helps understand is that what controls different types of polarities of normal faults in salt tectonics. We see that the basinward deep normal faults, they tend to form earlier and in a more proximal domain because it's mostly basinward zipping and without any barrier to salt flow. We start develop landward zipping normal faults later as you actually start prograding and differential loading becomes more efficient. And they tend to form usually in areas that the salt was originally thicker as well. So basinward zipping normal faults form preferentially where the salt was thinner and seaward zipping. And the landward zipping normal faults, the opposite. So you have these extensional rollovers, which are usually, you can readily associate them on basinward zipping normal faults, but expulsion rollovers are a bit different. They are a bit more complex. They have what we call some upturn, some near diapia upturn. So they are not just a simple thickening wedge. They thicken, then they thin against a diapia, and they usually vary a lot in terms of geometry. So you see here have strata thinning against the diapia, and then they thicken against the diapia, and then they are also upturned. And we also have turtle structures, and they can be, in the case of the second section here, just sort of mini basin, the welds, and then you have subsidence in the flanks of the mini basin, and then you create the turtle. But you also have turtle structures forming by the interplay between extension and expulsion. So the model helps shed lights on what controls some of the structural variability, both across or down deep and also along strike. And I think just to summarize the findings of these models, that we can expand on the previous work that shows the role of gliding and basal relief. Our models show that the spread in differential loads can influence or can enhance some of this basal relief effect by, for example, amplifying these flux variations that you have in a pure gliding scenario. We can actually help diapia break through this area of inflation. So you not only just have folding and contraction, you can actually have diapia breaking through the area. It can also change the polarity of normal faults because, as I mentioned, the differential loading start to influence these polarities. And in later stages, the effects of loading and spreading can actually reverse some of the effects that you'd expect with a pure gliding scenario. So areas that would initially be just associated with salt inflation and shortening can actually start to extend and develop extensional rollovers, for example, as you prograde the sediment seaward, so as the deformation migrates seaward. Just a quick sort of going on a tangent here, but kind of showing something that relates to what I've done with the modeling, with the physical model, and also linking to what Ollie will present in the next talk, which is something I've been currently working with. It's 2D numerical models of salt tectonics. And it kind of links because the really good thing about analog models is that we can see things in 3D. You can also do numerical models in 3D, but we're not quite there yet for salt tectonics. But we can test other things, and you can actually run the models at a very large scale. In this case, a full, well, an entire margin, but also conjugate margin scale. So I'm just going to show, I'm just going to run this video if I manage to. Yeah. So this is a model of a wide rifted margin formation where we deposit the salt at the very final stages of rifting. Have very thin rift sedimentation, so it's hard to see in this scale. But we have about 3 kilometers thick salt. I think the video just froze. So I'm gonna run again. I actually can stop here. So deposit salt when most of the crust has been stretched, and extension is really focused on the point of breakup, on the spreading center there. And as deposit the salt, you actually have some minor extension in this portion because you are stretching the salt and actually have to break up these conjugate salt basins and to become 2 separate basins. And then once we start, after the salt is deposited, we start prograding sediments, and we have the effects of gliding and spreading. So we can generate features like we see. I'm going to play that again quickly. In the Albion Gap, we have these very large rollovers, which are formed by a combination of salt expulsion and extension of the overburden. Have a domain of diapirs and a lot of shortening and some quite complex mini basins. I have a similar style of deformation in the other margin. And I forgot to mention, so this is the setup we use. So very large lithosphere scale models, thermomechanically coupled. So there's a lot of things that I can't really talk about it today, but I just wanted to give a quick snapshot of what I've been doing, and which is also modeling related, and yeah, relevant for the talk. So yeah, we can do these type of models for different margin types. You can assess different salt behaviors, rheological behavior, viscosities, and so on, and sedimentation rates, and etc. So we can compare these if we keep everything constant and just vary the margin geometry. We see a lot of different styles of deformation. And these are basically controlled by the salt thickness and volume on each of those margin types, and also the dimension of the margin itself, which the wider the margin is, the longer it takes for the sediments to cover and prograde over the entire margin. So you have this interplay between width of the margin, progradation rate, and also basal relief. So in this sort of narrower margin types, you usually tend to have a higher relief, which in many cases segments the salt basins completely. Whereas in the wider margins, like similar to what we see in Brazil and West Africa, the relief is more subtle, but it still influences the salt flow. And just to finalize, kind of trying to make the link with Ollie's talk, you have this very crazy salt deformation that we can actually, one of the things I mentioned before is that we can include different salt rheologies within the salt sequence. And by just varying viscosity, or for example, viscosity and density, we can have a very complex pattern of salt deformation within the salt. And that's something that we can't usually see in the data itself. The seismic data is very hard to image intra-salt sequences or deformation. Apart from very exceptional cases like the Santos Basin here, our study area, we have a lot of intra-salt complexity. So the salt is the whole LAS thing, which is layered evaporite sequence, and see a lot of complexities within the salt that kind of fits well with what we see in the models. And the other examples are salt mines, which you can actually control really well how these intra-salt heterogeneities are deformed in different ways. And with that, I can finish my talk. I will just leave you with the conclusions. I think I'm a bit behind time. So yeah, thank you.